Okay, so last part of the second order systems is the tank of ooh, is the tanks of fluid in series. In series. Okay. So remember in the first order system we had one tank like this, but now we have two of them in series like this. Okay, so say here is H1, potential of the fluid. What happened? Okay. Here is H1, here is H2. This expansion gonna act, say, as resistor here, absolute contraction. This contraction gonna be R2, and you have the tank CT1, CT2 capacity, and then you have inlet flow rate, and you have Q out flow rate. Okay. So what we're gonna do, we're gonna have the closed loop transfer function of Q in over Q out. Output, sorry, this is inverse. We're gonna have Q out over Q in, closed loop transfer functions. So remember that we had in electrical engineering we is called to RI, as we did the first order system, which is the potential, resistor, and the current. And we had I was C dV over dt for the capacitor. So we are taking the advantage of this analogy from the electrical engineering to go over tanks of fluid. So for the first tank here, so we have H1 equals to what? R1 in Q in. Q is I, R is R1, and H is this. And but when this comes here, guys, you have this intermediate flow here, say between this tank, say QA or QT transition. Let me name it as QN. QT transition. So now I'm applying this. So what you're gonna have, you're gonna have Qn minus Qt equals to C tank 1 dH1 over dt. This is for first tank. Okay. Now let us go here. So H2 equals to okay, R2 Q out, right? Hmm. And now Qt minus Q out gonna be C tank 2 dH2 over dt. Everybody understand? Yes? So what I'm gonna do, I'm gonna replace this H1 here. So you wanna have Qn minus Qt gonna be Ct1 R1 dQn over dt. And I'm gonna put H2 here. So you're gonna have Qt minus Q out gonna be Ct2 R2 dQ out over dt. Everybody understand? So do you think what I have done is correct? I give you 5 minutes. Just look at the picture. Just look at the picture. Yeah. Yes. So what do you think, guys? Do you think what I have done step by step is correct now? Hmm? Think about this. Okay. So to show that it's not correct, let me continue. I put Qt, okay, from here inside here. So you want to have Q in minus Q out plus CT2 R2 dQ out over dt is CT1 R1 dQ in over dt. Okay? So it's supposed to be second order systems, right? I mean the denominator must be s squared like that. Do you see here a second order time derivative? Do you see? No. You see s only if I apply the Laplace transform. Now I want to give you time, 5 minutes, to find out which of these are not right. after teaching you too many things in this class. 5 minutes from now. If you find, let me know. Anyone? So I want to assign this as a homework because this is good for your midterm, guys. Find what is the mistake that we get first order system, not second order system. Okay? Understand everyone? What is mistake? But the mistake you have to look at here. I'm giving you hints. There we go. Let me give you a hint, guys. What if I write, try this at home. I write here H1 minus H2 is R1 Qn. What if like that? Think about this. Think about this. Okay. Do it as a homework. So we are done with the second order system, guys. Let's go to higher order systems. The first higher order system that you may see is the 2 degree of freedom mass spring system like that. Here we go. K1, K2, and the K3, M1 and M2. Okay. I'm going to apply force here on the mass one, F1, and I'm going to apply a control force here, F2. So this is going to move as X1, this moves as X2. Okay. So I'm assuming that the X1, just assumption, is greater than the X2. If I do that, you're going to stretch K1, yeah, K2 and K3 gonna be compressed. That's right. So if you plot the free body diagram of this, as you have to do in dynamics always, you have to cut the system from here, and from here. So for mass one, you have a resistance spring force because we are taking this way. It's going to be K x1. For here, you're going to have a pushing because you're pushing this way. It's going to be this way. There's Q2 x1 minus x2 because the spring is middle between them. Guys, look at me. What I wrote, go and apply here. That's a hint, okay? And now this way for the second mass. Based on the Newton's second law, action and reaction forces. So you're gonna have for this exactly the same value in the opposite direction. K2 x1 minus x2. And here, because you are pushing this way, you're gonna have this K3 x2, because the spring is only affected by x2 here. The spring is only affected by x1, but this spring is affected by x1 and x2. Okay, so now I'm going to apply Newton's second law for two masses. Sum of the forces in x direction is mx double dot. We have two masses, two equations. So we're going to have this m1 x double dot 1 equals to, okay, this is positive this way is negative. Positive, negative. This is our coordinate system. So this is going to be negative force minus k1 x1, negative force minus k2 x1 minus x2. What I'm going to calculate, I want to calculate x1 over f1 and x2 over f2 as a closed transfer function. And this external force is positive way, plus f1. Equation number 1. The other one is m2 x double dot 2 equals to, now this is in the positive direction. This is going to be k2 x1 minus x2 negative minus k3 x2 plus f2. Here we go. Let me first calculate this. For doing that, I have to apply the Laplace on the both sides of these equations. Assuming that the x1 at time 0 is equal to x2 at time 0 is 0 for Laplace, and the velocities of masses at time 0 is 0 again. Okay, so you're gonna have m1 s squared because second time derivative x1 equals to, now if you just summarize everything, you're gonna get k1 plus k2 x1, okay, and now plus k2 x2 minus and minus plus f1 of s, obviously. The same is here. m2 s squared x2 gonna be here minus k2 plus k3 x2 minus k2 plus k2 x1 plus f2. Okay, so I want to find x1 over f1, the displacement of mass 1 subject to its force, its own force. So what I'm gonna do, I have to calculate x2 from this equation and implement here, right, everybody? So for simplicity, I'm assuming f2 is 0. Only I have this f1. So I'm just removing f2 from here. There's no f2 for simplicity of teaching. So from here you get, if you move to other side, you get x2 gonna be m2 s squared plus k2 plus k3 equals to k2 x1. So from here I found x2 gonna be k2 x1 in m2 s squared plus k2 plus k3. Now what I'm gonna do, I'm gonna implement this inside here. There we go. Okay, let us do that. Oh no. Okay. If that the case is, I'm gonna open another PowerPoint. Okay. So from previous one, can you please this for me, guys? Any of you? This line, this line. Can you read for me? M1 s square x1 was equal to how much? K1 plus K2 in x1 plus K2 x2 plus f1. Yes, it was like this, right? Okay. And we found x2 was how much? X2 was K2 x1 divided by M2 s square plus K2 plus K3. Yes? No, second power. How we got this one? X double dot. Okay? X double dot. So let's implement there. So we're gonna have M1 s square x1 gonna be minus K1 plus K2 in x1 plus K2 square x1 divided by M2 s square plus K2 plus K3 plus F1. Now what I'm gonna do, I'm gonna move this term and this term to the other side. So if I do that, you get x1, then m1 s square multiplied by m2 s square plus k2 plus k3 plus k1 plus k2 again in m2 s square plus k2 plus k3, okay, plus k2 square and m2s square plus k2 plus k3. Here we go. Everybody agree? And this is equal to how much? F1. So now, as we expect, we have fourth order system. So if I want to simplify everything, so I'm going to say M1, M2, S4. Now we have higher order system. Plus, so S, we don't have S square, only S. So you're going to have M1, K2 plus K3 from here, S square, plus K1 plus K2 M2 from here, and this is S square and the only numbers are K2 square plus K1 plus K2 in K2 plus K3 equals to F1 multiplied by M2S square plus K2 plus K3. There we go. So the closed transfer function of x1 over f1, or stay open loop transfer function here, I'm gonna tell you why. Gonna be m2 m2 s square plus k2 plus k3 divided by m1 m2 s4 plus m1 k2 plus k3 plus k2 plus k1 m2 s square plus k2 square plus k1 plus k2 plus k3. Bingo. Okay. Now let me think. M1 and M2, they are both 1 kilogram, for God's sake. And K1 equals to K2 equals to K3 equals to, I don't know, 100 Newton per meter. They are equal things, that's right. So if you're right, if you are done, let me know. I'm gonna move to the next page. Are you done? Okay. So having said, I'm gonna simplify this as x1 over f1 gonna be, so s square plus 200 gonna be, for example, s square plus 200 divided by s f s4 fourth order plus, so okay, 200 plus 200, 400 s square, and K2 square means 10,000 plus again gonna be, see here, it's gonna be 200 multiplied by 200. It's gonna be how much? 40,000. 10,000, 50,000. Gonna be 50,000. Everybody agree? Yes? Everybody agree? So without solving this system, high order system, I promise you $10 million, that system gonna oscillate forever. This system under by looking at this transfer function, I bet gonna oscillate forever before going to the MATLAB. Okay. First of all, how many zeros this system has, and how many poles has? How many zeros the system has? Huh? These are the zeros. How many zeros it has? Guys, Z1 and 2 gonna be plus minus I 200. Right, everyone? Yes? Huh? So how many poles this has? Guys? How many poles? Yes? How many poles, guys? Hello? Disconnected? Yes. P4, P3, P4. So now here we're gonna go to the MATLAB. Not for this problem, for every problem that you're gonna see after this, after graduation, how to solve this in MATLAB, these poles, because maybe you have S10, S100 in some systems. You cannot solve it by hand. Okay. Okay, so what you're gonna do, you're gonna say sims, you're gonna type it here as sims, oh my god, sims variable x, okay, because we're gonna solve that equation. Hold a little. Okay, after that say solve. This is how MATLAB works. X to the power of 4 plus, what was the coefficients? 400 multiplied by x square plus 50,000. And this is gonna solve for you. This is the answer. But you can say double ans. It's gonna give you this. So you have a pair of complex conjugate poles, guys, here. See? With the real part negative, complex conjugate poles here with the positive real part. So you're gonna have this, guys. If I wanna plot it. So we have this system, zeros and poles are like this. Real, imaginary. Okay. So you have two zeros here, say it is 100, 200. You have two zeros here. Here, a pair of zeros. We are showing zeros with this. And you have, based on MATLAB, plus 3, 4, minus 4, like this. So say here is plus 3, 4, and a pair of complex conjugate pole here on the right hand side, and exactly the same on the left hand side. See? Minus 3 plus 3. Minus 14 plus 14. So as I taught you, whatever is in the right hand side means your system is what? Unstable. Whatever here says is stable. Whatever poles are the imaginary means your system is marginally stable. Okay? It's marginally stable. So, but these are not the poles, these are zeros located here. So that's why, okay, I want to give a step to this step function, to this high order system. Okay, and plot it in the Simulink. Okay. Okay, let's see how it behaves. Okay. So what I'm gonna do, I'm gonna just copy this, put a new this here, and then remove all of those. I'm gonna change this to, okay, it was fourth order system, so you're gonna have here 0, 0, 1, and 0, and what was the constant number in the numerator? 200. 200. And denominator was S4, S cubed, there is no S cubed. What was the coefficient of that? S square? What was that? S square? Huh? Okay. And there is no S. And what was the, so 50,000, right? Yes? So this is S for 1, S4, S cube, S square, S, and constant number. See how I wrote it? Do you see that? Because numerator and denominator, they must be what? The same, I mean in the notations. So this is our transfer function. Then I'm gonna remove this with a step. A step. And I'm gonna plot this. Step times 0. And I'm gonna save this in ME40 fourth order system. Fourth order system. Just let me double check this again. 0, 0, 1, 0, 400, 50,000. Okay. Then I'm gonna plot it, and there's no need for this to be amplified. So if I run this, Here we go. System becomes, this yellow line becomes, system becomes what? Unstable. Because of that what? That the pair of complex conjugate poles is oscillating but unstable. Right? Let me increase time to show you. Here we go. It becomes unstable at the end. Understand? This becomes unstable. Goes to wherever. Okay? And oscillating and obviously unstable. Okay? So that's it. Now you know it. That's it. Okay, guys. Okay. So, and that instability comes from these poles on the right hand side. Okay. And these are the zeros of the system, and this is the stable poles of the system. Clear, everybody? Yes? Okay, guys, now you let me know. What if, let me show you. What if I have three masses here? What's gonna be order of the system? Two masses, order of the system became how much? 4. Now, if I have three masses, what's gonna be order of the system? 2 became 4. 3 becomes 6. 4 becomes 8. N becomes N mass becomes no 2n. Okay, if you have n masses here in the series, you're gonna have 2nth order system. If you have 10 mass, we're gonna have 20th order system, meaning that if we have 20 mass, if we have 20 mass in series, 1, 2, 3, by a spring connected together, the transfer function gonna be say S40 plus whatever. So you're gonna have 40 poles. This is my point. 40 poles. See what I'm saying? If you have, I don't know, 50 mass, you're gonna have S100. You're gonna have 100 poles. You cannot solve by hand. What you're gonna do? You have to go to the MATLAB. Use this command. Solve and solve it. For example, if you have such a system, you have, I don't know, you have 10 mass, so you're gonna be S20 plus 5,000. These are just numbers. S10 plus 200,000. And this is not S, this is X. And you can say double to make it visible. Double ends. See, these are 20 poles of the system. In the right hand side, complex, right hand side, right hand side, right hand side, right hand side means the system is unstable. Left hand side, this is complex conjugate. This is imaginary poles. Left hand side, this is imaginary poles. Left hand side, left hand side, left hand side. See, so you have 20 of poles of the system. So it doesn't matter what's the order of the system. You can use MATLAB and judge the system before plotting. We're seeing that you have many right-hand poles. It says that your system is unstable. So you need controller. Where? At ME430 control class to fix it. See what I'm saying, everybody? Yes. So next class we're going to continue. After break we're going to continue the higher order system. Any questions?